This video is about exponential growth and exponential decay. We're going to spend a lot of time talking about how to use the calculator as well. So these first three problems, I already have all of the hand work done. So for number one, we would change everything into base 2 because 64, 16, and 8 are all powers of 2. And then we use some exponent rules, power to a power, multiply the exponents. When we divide two things with the same base, we subtract the exponents, and then because we have a 2 base on both sides, we can set the insides equal to each other, or I'm sorry, the powers equal to each other, the exponents, and then solve. So we get x equals 3.5 or 7 halves. Number 2, we would just take a log base 2 of both sides. Number 3, we would take a log of both sides. You could choose whichever base you wanted. Choosing base 5 or base 3 might be a little bit easier to look at, but I chose natural log because on a previous video I did it with log of a base of one of these numbers. And so you then distribute out, you try to get all the x's on one side, everything without an x on the other side, and then you factor out and divide. The thing that we're going to try and talk about today is how do we solve these if it's a calculator portion of the test? Because we don't really need to do things like all of this handwritten stuff if this problem is on the calculator part of the test. So if it's on the calculator part of the test and we just want to get an answer, what we would do, for example, in number 2, is we could just take 2 to the x and 5, and then type them in y1 and y2 and find the intersection. So you just take both sides of the equal sign, type them in as y1 and y2, and then you find the intersection of those two things, and you find it's 2.322, and 2.322 is 3 decimal place rounded of log base 2 of 5. Same thing for number 3, 5 to the x minus 2. We'd say 5 to the x minus 2. And we would say 3 to the x plus 2. I think that was what the problem was. Oh, 3x plus 2. Sorry. And then we graph that. And then we realize, oh my goodness, well, this is not going to cut it because I can't find the intersection anywhere. So what I would have to do is change my window, and that's clearly going to be very, very high up there. So let's try 1,000. And that's still not going to get it done. Actually, it might even be a negative number, so a negative x value. So let's try that. And actually, that's what it is. So thankfully, what we see is that if I can't find the intersection, maybe it was over at some negative x value. So negative 3.212 ended up being what this would be. Here. And that's a really important concept for us to understand, is that if we type both of these things in as y1 and y2, then find the intersection, we can actually do a lot of this quicker on a calculator part of the test. Not that any of this stuff that's written down is wrong, but it just takes a lot of time if it's a calculator part of the test. So we have growth and decay formulas. We're pretty familiar with y equals ab to the x. A new one that we're going to talk about is y, or a, equals a sub 0, or a naught, that's the initial value, times e to the kt. And you can convert between these things because the initial value on the right side has to be equal to the initial value on the left side, because those two things are the same. And clearly the variables are going to be t and x are the same. So that leaves us with b has to equal e to the k. So if we have something written in this format, we can convert it to the format with a base of e by setting b equal to e to the k. Then another question that we need to ask is, how do we determine whether this is growing or decaying? And we clearly can see that up here. So if it's y equals a times b to the x, if b is bigger than 1, we have a growth model. If it is between 0 and 1, we have a decay model. And if b is negative, we have a model that is very difficult to deal with. We never really deal with that stuff because, for example, if I had negative 2 to the x, every time x is even, it would be positive, and every time x is odd, it would be negative, and that would be a graph that's just unsustainable for us, especially when you're dealing with fractions in the exponent. Which fractions are even and which are odd? It's kind of tough to tell. Over here, when k is positive, you have a growth model. When k is negative, you have a decay model. And when k is 0, this doesn't make any sense because the whole thing would go away, right? E to the 0 would be 1, and then you just have a equals a constant. So that determines the growth or decay. Traces of burned wood along with ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. So carbon-14 is used in trying to date things that are pretty old. If the half-life of carbon-14 is 5,600 years, approximately when was the tree cut and burned? So we would use this formula that we're pretty familiar with. The amount is equal to the initial amount times 1/2 to the t over however long the half-life is. And the reason for that is if the half-life is, for example, 5,600 years, if I plug in t equals 5,600, that would mean exactly half of this goes away, right? Because I'm multiplying the initial amount by 1/2. Now, if we want to convert this to the e to the kt formula, in y equals a b to the x, notice that in our half-life formula, b is equal to 1/2 to the 1 over t to the 1/2, so, or t sub 1/2. That's the half-life constant, or the half-life, like in this case, it would be 5,600. So, since b equals e to the k, I can solve for k and get this into the half-life, get this into the e format. And so I can rewrite this as a equals a sub 0 times e to the natural log of 1/2 over 5,600 t. So this is all the exponent. So notice I just did a little calculation and I could rewrite it with a base of e. Neither one is better or worse, but sometimes with a base of e, it just shows up in more textbooks and it shows up a lot in science classes and things like that. So it's important to understand how to do that. The other thing is when you get into calculus, things with base e work a lot better for taking derivatives and integrals. So it's nice to see formulas with e to the power of something. Now for this particular problem, it doesn't matter what we start with. We could have 100 grams of a tree or 5,000 grams of a tree or whatever, but we don't know how much carbon-14 there was originally. We just figure that there's about 1.67% of the original amount. So all that we really need to know is how much remains, not how much was there originally. So the amount is equal to 1.67% times the initial amount. So when I rewrite the formula, I can just say that the amount is equal to 0.0167, and then the a's end up canceling out, essentially. And then that's equal to this, and then I do a little bit of algebra, taking natural log of both sides, multiplying by 5600, dividing by natural log of 1/2, and I can get 33,062.445 years. But I could also do this on the calculator, and so I have the formula, which we'll just assume there's 100% to start. So then I have e to the natural log of 1/2 t over 5600 and then I want to set this equal to 0.0167. So as I look for this, I know kind of what my answer is going to be because I already did it, but if I were doing this on the test, I would need my x max to be very large, and I do not want my y max to be very big. So I know that it's biggest at 1 and its smallest is 0, because I can't possibly get any smaller than 0%, right? So then I would find the intersection with second calc intersect. And then I get the answer. Now for the rest of the time, I'm going to assume that you don't need me to type those in, and I'll just show pictures of that to make the video a little bit shorter. Strontium-90 is a radioactive material that decays according to this function. What is the half-life of strontium with T in years? So if we remember that after we just kind of figured out what happens with half-life, the constant in this e to the kt thing for half-life is the natural log of 1/2 over whatever the half-life is. And I know that the constant here is negative 0.0244. I just do a little cross multiplying and I end up with the half-life is the natural log of 1/2 over negative 0.0244. Type that in the calculator, I get 28.407 years. Now, one other thing that may be important to be aware of is that natural log of 1/2 and natural log of 2 are opposites, and that's just a log rule, right? Because if I have the natural log of 1/2, that's equal to the natural log of 1 minus the natural log of 2 using our log properties. Natural log of 1 is 0. So these two things are the same. Because of that, I can use either natural log of 1/2 or negative natural log of 2 in any of these formulas that I have. So this is also equal to the natural log of 2 over positive 0.0244. Kind of just depends on how you want to do it. Problem 3, colony of bacteria increases according to the law of uninhibited growth. And if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture for t with the time in hours. So I'm going to call t sub 2 doubling time. So instead of half-life, it's basically double life. How fast does it grow? Double. And so instead of a 1/2 in here, it'll be a 2. If I wanted to convert this to the E formula, so e to the k would equal 2 to the 1 over the doubling time. So k is equal to natural log of 2 over the doubling time. So that would be natural log of 2 over 3 in this case, because the doubling time is 3. So these are the two equations that we'd see. How long would it take for the size of the colony to triple? We would have to replace a with 3 and a sub 0 with 1, because we want it to be 3 times as big as it initially was. So we just make those replacements, and then we can solve these functions for t by hand. It would look like this. On the calculator, you could just type either of these in, or you could type 2 to the t over 3 in for y1 and 3 in for y2 and make those solving on the calculator. Number 4, a chemist has a 100-gram sample of radioactive material. He records the amount of radioactive material every week for 6 weeks and gets this data. Now, exponential regression looks like this, but I'm going to remind us real briefly how to do that. We hit the stat button, Then we hit edit. Then we type in all of our data. I'm not going to type in the data again, just to save you guys time. But then I hit the stat button again after you type it in. And then we want an exponential regression, because this is exponential growth or decay. So you go to 0 on your TI calculator, which is exponential regression. L1, L2, if you want to store it as Y1, you hit vars function Y1. Then you hit calculate. You've seen this many times with regression, and then you end up with the data. So that data shows up here, and that makes your equation. Now you want to keep as many decimal places as possible, especially in exponential stuff, because once you start trimming off decimal places and you take something to a large x power, it's going to be very different. So you want to keep as many decimal places as your calculator gives you. So remember what we learned at the beginning of the video. If I have y equals a times b to the x, and a equals a sub 0 e to the kt, the initial amounts are the same, t equals x, so that means that e to the k equals b. Since e to the k equals b, b is this thing, I do a little algebra, k equals the natural log of that, which if I type it in the calculator is negative 0.1314, and so on. So this is my new function with e as the base. If I want to find the half-life, I have to realize that the half-life, since I started with 100, 50 is going to occur somewhere in here. So this should occur somewhere between 5 and 6 weeks. So I replace this a with 50, basically, or 50 point whatever, but I want this to equal 1/2, right? So this equals 1/2 because a should be exactly half as big as a naught. And then I have e to this power t. Then I do a little solving. Either take a natural log of both sides, so natural log of 1/2, and then divide by negative 0.13140211, which is k. Then I get 5.275 weeks. Or I could also do this on the calculator. If I typed this in for y1, or the red version of it, type it in for y1, and then I have to do 100.326250.8 divided by 2 in for y2, then find the intersection. The amount of radioactive material left after 50 weeks, you plug 50 in for x, or 50 in for t, and then you get the answer. That's just done on the calculator. It's not too hard. We have one last problem. Hospitals utilizing radioactive substance, iodine-131, in thyroid gland diagnosis. Half-life is 8 days. If there's a sample of 2 grams, how much will be left after 20 days? You can write the function with the 1/2 as b, or we can use e to the natural log of 1/2 over 8, because remember 8 is the half-life. Then after 20 days, so t equals 20. So you plug t equals 20 into either of these equations, plug it in the calculator, you get 0.354 grams. That's rounded to 3 decimal places. How long will it be till only 1/100th of a gram remains? So you would plug 0.01 in for y. You can do this 2 ways. You can solve by hand, and you can get 8 times log base 1/2 of 0.005. That's fine, but if it's on the calculator part of a test, I'd recommend just using your calculator. So you plug 0.01 in for y, and then 2 to the 1/2, or 2 times 1/2 to the x over 8, or the e version of it. So this one over here, in for y1, either case. You graph both of them. Notice I had to change the window in order to make it fit. You just had to make sure that you include the answer in x in your window. And then notice that y is not going to be any bigger than 2, right? So it's going to be pretty small. And then you just find the intersection again, and you get 65.151 days, which is equivalent to whatever this is.